Okay. Hi everyone. I introduced my dad in the statistical machine learning course, but in deep learning course also he is my dad, Yusef, and I'm happy to have him as my guest today. Thank you very much. See the video. Thank you very much. I appreciate it.
That's
Yusef, pleasure. Thank you. Okay, so let me share screen. Okay, great. I think now we are. So, hi everyone. As we said, so in the previous session, we talked about backpropagation and these things, and now we went a bit to the regularization, but I got stuck in there. I got confused a bit, but we will resume that. And today we are going to talk about regularization in deep learning, and then convolutional neural networks and some important convolutional neural networks. And if we have time, we will go over other architectures such as recurrent neural network and LSTM. Okay, any question before? By the way, very soon I will post your assignment 1. So for a statistical machine learning course, I already posted that because that's a session ahead from this deep learning. But yeah, I think I will also post some announcements for group teams, group projects. But I think it's a good time to start forming the teams. I will tell you the details in the course link. Okay. And I think in several weeks, maybe 2-3 weeks, we'll have the midterm. I'm not restricted to put the midterm in the middle of the term. It can be a bit after the middle of the term, but be prepared for that. Start studying for that. And the reason for assignment is not only it's a part of the grading, although I think you know my style. Grading is not hard in this course, but although it's a part of the grading, it also gives you some example questions for the midterm, because you will see the style of questions. In the statistical machine learning course, for example, the style of questions is like using the algorithms for some machine learning tasks, such as classification, regression, and these things. So I'm not asking proofs. Here also, I don't ask proofs. In deep learning course, the questions will be, you will see in the assignments, but to give you some rough idea. So for example, I will say we have a neural network, maybe with several layers, with a few neurons, and these are some data points. Do 2 iterations or several iterations of backpropagation, for example, with this learning rate. Do the Adam 1 iteration or so. So there is no proof, as you see. Also, I'm deciding to make both of the courses, their exams open book. So you don't, because I hate memorization. I don't memorize too. So you will be able to see the formulas and these things. So there is no memorization, just understand. You need to understand the algorithms to be able to use them in the assignment and also the exam. And I will be there. I will be in the midterm. It will be in person. I will be there the whole time. I will give you extra time if you need that. And whenever you have any question, you can ask, and I will answer to everyone. So it will be fair. Okay. So as I said, yeah. And for example, as you will see in the assignment, maybe several iterations of backpropagation, Adam, and these things, or several iterations of logistic regression, or doing RBF network. These not proof, just using them. Okay. But for using them, you need to understand. Don't skip the derivations. Understand how it is working, okay? And then you can easily use them. And also, as I said, it will be open book for both courses. So let me continue. So regularization, we already talked about regularization in general for machine learning in the additional video that I posted on YouTube. I asked you to watch that. So please watch this. It's available in this link. It's overfitting, cross-validation, regularization, and L1 and L2 norm regularization in machine learning. But there are some specific methods just for deep learning. One of them is weight decay, okay? So what is with weight decay? It says that let's have add a penalty to what? To the length of the weights so they don't explode. So I want my weights to be small enough. I don't want them to be big. So assume your objective function or your cost function, your loss function is J. W here denotes all of the weights of the neural network. Theta here you can ignore it, but some parameters that can be in the loss function, which are not the optimization variables. Alpha over 2. Alpha is the regularization parameter. It must be greater than 0. It shouldn't be negative, because if it is negative, then minimization becomes maximization, and it will explode the L2 norm of the weights. And this is L2 squared L2 norm of the weights if you consider the weights as vector. So you concatenate all of the weights as one vector here in this notation, okay? If you consider them as a matrix, then it will be squared Frobenius. And this 2 in the denominator is because its derivative will be 2w, and I want that 2 to be cancelled. Okay. And penalizing the weights with regularization is referred to as weight decay, as we saw here. Okay, this penalty prevents neural network from becoming too nonlinear and thus overfitting. And I briefly mentioned that in the previous session too, where most of the activation functions are almost linear, close to 0, like consider the hyperbolic tangent, close to linear, around 0. But with the further we get from the 0, the more nonlinear they become. So therefore, we don't want the weights to be big, because if the weights are big, then the output of the layer or the input of the next layer will be big. So they will fall in the nonlinear regions, more nonlinear regions of the activation functions. And it means that the network becomes too nonlinear. Of course, we don't want too linear, because it needs to handle nonlinearity of data. We don't want it to be too nonlinear, because it means that the variance is high, therefore it's overfitting. So we want a middle case scenario. So, and that's why we do weight decay. Also, as I said, I already explained this paragraph. Now, we say all the neural networks should not be completely linear, because we want to handle nonlinear patterns. Yes. And penalizing the weights makes the weights relatively small. So we are in the almost linear regions of the activation functions. Now, another analysis of that is that in the lecture of overfitting, we proved that the result of equation 1, which is this, is this. What do you remember if you have watched that video? Let's take a look at that. W star is the minimizer of J. So if you just minimize J, that would give you W star. So derivative of J with respect to W, set it to 0, it gives you W star. And assume the Hessian of J, which is this Hessian matrix of the J. We apply eigenvalue decomposition on that, and we will get U and V as the eigenvectors and eigenvalues of the Hessian of J. Okay. So H, or Hessian of J, is U delta U transpose. Then these U's and deltas come from the eigenvalue decomposition of the Hessian. This alpha is the regularization parameter here. This I is the identity matrix, and this is inverse. So we proved that. If you want to see where it was, let me go to that slide. It was here. So take it. I'm now in the slide deck for the regularization in machine learning, which we covered already. So if you remember, we are minimizing J tilde equals J plus alpha over 2 square delta norm of X. Here, the optimization variable is X. There, in weight decay, it was W. Okay. And then we said, let's write the Taylor series expansion of J and estimate J with J hat. The first term will be 0. We discussed that because J of X star is 0, because we know that X star, the gradient of J at X0 is 0 because of first order optimality condition, because at X star, J is minimized, so its derivative should be 0 at that point. And then we worked it out, and we ended up with equation 29, which I have mentioned in that slide too. So recall this, and then I have said in that slide that we have the same analysis as we did here. What was the analysis? So we said that, do you remember this term in the middle is here, repeated here. We can analyze that as discussed in this slide. This is the term appeared there. And what does it say? We have 2 bullet points here. So elements wise, it's like this because it's a diagonal matrix. Because why? Because delta is diagonal, I is also diagonal, inverse of a diagonal matrix is diagonal. This delta is also diagonal. Diagonal times diagonal is also diagonal. Okay. So we have this, and as you see, if 2 cases, if delta J for one of them, so we have J from 1 to D, right? For each of them. If delta J is much greater than alpha, then delta J over delta J plus alpha is almost 1, right? So that one of these terms becomes 1 for that. It means that we care about that. We care about why? Because when does it happen? When delta J is much greater than alpha, it means that delta J is large, right? And what was delta J? Was the eigenvalue of the Hessian. Okay. And when the eigenvalue of the Hessian is strong, it means that the Jth direction of J itself is strong. So we should care about that. Therefore, it becomes almost 1. However, if delta J is small, it means that the Jth direction of the cost is small. We shouldn't care much about it. And then that dampens to almost 0. Delta J over delta J plus alpha becomes almost 0. So this is the analysis. Again, we have the same analysis there. So when we are doing weight decay, we care with 1 by 1 each dimension of the cost function. We see which one we should care and which one we shouldn't care. We should dampen it. And what dampens that? The penalty is dampening it because of alpha, right? Alpha is the regularization parameter, so it dampens that to 0. Okay, so let's go back to that slide. Okay, now noise injection to input in neural networks. So in training neural networks, it is beneficial to add noise to the input. One perspective to why adding noise to input helps better training of network is data augmentation. So one technique for regularization was weight decay, which we talked about. Another one is noise injection to the input. So we have an input data set. We can add noise to some of the data points, or we can duplicate some of the data points and add to the duplicated ones. So in this way, we can see it as data augmentation. We are adding to the data. And why is it useful? Because when you have a data set, when your network is too small, what happens? Assume you don't have enough number of layers. What happens? Underfitting. Underfitting happens because you don't have enough parameters to learn. If you make the number of layers, if you increase the number of layers or the number of neurons, so implicitly you are increasing the number of weights, the number of parameters. Therefore, you will have overfitting. In order to prevent overfitting, you need bigger data sets. Okay, so the more parameters you have, you need the more data you have in order not to have overfitting to your training data. So for that, you augment to your data. We have different types of data augmentation. One of them is noise injection to input. So another one might be rotation, might be translation, and these things. So you take some of your data points, just translate some of them a bit. You rotate them a bit, or you have a combination of rotation and translation. You add noise, or you have a combination of all of these. So you can write your own module for data augmentation, although PyTorch and all of these already have them. So you can use them for in your data loader or in the data preparation module. So you give your data set to that module, and you'll say, okay, randomly, you can code that. You can say randomly with some probability, don't do anything to the data. With some probability, add Gaussian noise to it. With some probability, translate it a bit. With some probability, rotate it. With some probability, do a combination of these. With some probability, crop some of the image, for example, and make it black. With some probability, crop some part of the image and make it white. And these things, okay? So there are various ways for doing data augmentation. Okay, so that was one thing. Okay, another interpretation for noise injection is regularization. And it's this. So assume this is a loss function J. We want to minimize J and let it be a least squares problem or mean squared error. So this is error, this is expectation is mean, and this is a square, right? Y hat is the output, predicted output by the neural network. Y is the actual labels. So we want Y hat to be close to Y. And expectation is the average because we are doing batch wise, right? So we have batches. And this is J. So this is the loss function. Assume we have some noise because it's noise injection, right? So we need to have some noise epsilon, which is Gaussian with mean 0 and variance sigma squared. I'm assuming that it is spherical in the space. So the off-diagonal elements of the covariance matrix of epsilon are 0. And why? Yeah, what does it mean, sigma squared I? It means that the dimensions are uncorrelated. So it's like a sphere, but or oval. But sigma squared, it means that on all dimensions, their variance is the same. Therefore, it's not oval. It's actually like a sphere, right? So, for example, in 2D, it's like this. For example, these off-diagonal elements are not 0, right? I'm right, because the two directions are correlated here. Here, the off-diagonal elements are 0, but they are not equal. The variances of the directions are not equal. So, for example, it's sigma 1 squared, sigma 2 squared, right? But here, this case, off-diagonal elements are 0, and they're both sigma squared. They're equal to each other. Okay, so that's the meaning. And so assume I have some noise. Basically, what it means is that add noise to different features, to all features, with some Gaussian distribution, and you don't care. For example, when you add noise to one feature, for the next feature, you don't care whether you added noise to the previous feature or not. Okay, so look at them independently and add noise to all of them with some variance sigma squared. Okay, so now we replace x, which is the input of the neural network, with x plus epsilon, because we are assuming this is additive noise, right? Noise injection. I'm saying that I'm adding noise because we might have multiple ways to apply noise to the data. We usually do adding, and that's called additive noise. So we have x plus epsilon. Now, using the binomial theorem, a plus b squared, a minus b squared is a squared plus b squared minus 2ab. I have this, so the first term squared, the second term squared minus 2, the first is times the second. Then expectation is a linear operator, therefore I can have expectation for each of them. 2 is a scalar, so 2 is not random and also scalar, so it can come out of the expectation. And then I say, okay, y hat, I have y hat, let me write a Taylor series expansion of y hat x plus epsilon, okay? And that would be like this, y hat x plus epsilon transpose derivative of y hat x with respect to x, plus this is now quadratic with respect to epsilon and y hat both. So 1 over 2 epsilon transpose second derivative of y hat with respect to x epsilon. So this term, as you see, is quadratic with respect to epsilon and derivative of y hat both. This term is linear with respect to both epsilon and derivative of y hat with respect to x. And there are other terms. Okay, and this is a small o complexity. Okay. So here, what did we have? I'm repeating them here. So we have j tilde. What is j tilde? The loss function for the noisy data, for the noisy. Okay. And y hat, this is the Taylor series expansion. Okay, I thought about this, which I got confused a lot. This is what I ended up with my analysis. But we can talk about it off class if you would like more. So first off, what am I doing? So this is j tilde, okay? This is y hat. I have y hat in j tilde in 2 places, here and here, okay? I have y hat of x plus epsilon. I know that this is a Taylor series expansion of y hat x plus epsilon. So I replace in this expression, I replace y hat x plus epsilon with its Taylor series expansion. What happens? So assume I go step by step because it's a bit confusing. This is the first term, second term, the third term, okay? So this is the first term. This big parenthesis is the second term. This is the third term, okay? Where I have replaced y hat x plus epsilon with its Taylor series expansion. Okay, so far clear. Now, in the first term, the first term, I have a squared. So I can use binomial theorem for expanding that. I mean, a plus b squared is a squared plus b squared plus 2ab. However, here I have quadratic form. By the binomial theorem, it becomes more, even with more degrees, okay? And epsilon is a small. Epsilon squared is a smaller. Epsilon cubed is much smaller. So for binomial theorem, I can ignore that, okay? I can ignore the third term. If I do that, then I will end up with only these 2 terms squared. So I have the first term squared, y hat x squared, plus the second term squared, epsilon transpose derivative of y hat x with respect to x squared, plus 2, the first one times the second. So far clear. Okay. So now this one. Also, as you know, expectation is linear. I can apply them on each of these terms. That's That's so far clear. Okay, now what do we do? I have put numbers behind them so you can find out what we have done. So this is 1, right? I have put it here. Okay. Then 2 is what? This is 2. I have put it here, right? Expectation of y hat, y squared. I have the third term. What is that? Here we have the third term. So I'm rearranging them, right? Back and forth, I can do that. So here, this is the third term. The fourth term is this. So here, as you see, we have -2 here, and 1/2 also. So -2 is here, and 1/2 is here. So the fourth term is here. So far clear? Okay. Now, what do we have? The fifth term, let me see. The fifth term is here. The fifth term, so I'm putting it here. Okay. Okay. Now, these two cancel each other. Right? These two cancel. So that's why I have put 6 under them. So these two, one of them is plus, one of them is minus. -2, right? Therefore, the 6 ones cancel each other. Now, what is the 7th one? I thought about it. I might be wrong, but as far as I have understood. Sorry. So the 7th term is this. Do you remember I ignored this term? Right? But this term, for binomial theorem, I ignored that. But this term can appear as this. So because this is my suggestion. This term, if you don't ignore that, it appears as this term. Okay, the 7th term. I thought about it for a long time. Where did this 7th term come from? But apparently it comes from the term that we ignored. Okay. So far, by rearranging and our calculations, we simplified J tilde to be this. Now, let's simplify this again further. How? Terms 1, 2, 3, consider them all together, is here. Okay. You can write it as the inverse of binomial theorem. So a squared plus b squared minus 2ab, I write it as a minus b squared. Okay. So I can write it in this way. What is this? Interestingly, that's j. J of x. Recall equation 3. Right? Interestingly, first, second, and third terms here are equal to j of x without noise. Loss function for the network without noise. Okay. Now, consider term 5. Term 5. I'm simplifying it here. Okay. I assume epsilon is independent of data, right? Therefore, epsilon is independent of the derivative of y hat with respect to x, right? So I can, and as it is quadratic, I can write it as epsilon transpose epsilon, because it's quadratic with respect to epsilon, and also it's quadratic with respect to derivative. So I can write it in this way. Note that this also is equal to squared L2 normal epsilon, right? Okay, so we have simplified everything. We have and this is sigma squared. Why is it sigma squared? Recall preliminaries. Just give me a second. Give me a second. this one. So I'm proving this. So I'm saying that expectation of, recall this, expectation of epsilon transpose epsilon equals variance of epsilon plus expectation of epsilon squared. Okay, this is the formula of variance, one of the formulas of variance. For more information, let's see the preliminaries on a statistical machine learning course. Okay, I have proved that there. Doesn't matter. This is a basic formula. So it's in other words, for scalar, variance of x equals expectation of x squared minus expectation of x squared. Okay, so this is 0 because the mean is 0, and this variance is sigma squared. So expectation of epsilon transpose epsilon is sigma, right? That's why I have sigma squared here, and this is the rest. Okay. Now, terms 7 and 4. So we talked about term 5. We talked about term 1 and 2 and 3. Now 7 and 4 are left, right? 4 and 7. Let's simplify them. So I'm writing them here. These twos cancel each other, so it becomes like this. Again, epsilon is independent of the data and the derivatives. So I can write it as this. I have epsilon transpose epsilon here. I bring it out. Also, I have the rest of the terms here. Here also epsilon transpose epsilon, I bring it out. I have the rest of the terms here, right? Now, we saw in the previous slide, this is sigma squared, this is sigma squared. I factor out sigma squared. I end up with this, okay? So put this, and this all together, which are all of the terms, which we simplify, you will end up with equation 4, okay? And now we ended up with an expression which we can analyze. We can analyze now. What does it say? It is a regularized optimization problem with L2 norm penalty. Why? So this is a penalty, right? We can also see this as kind of penalty. So J plus some penalty or regularization term. And interestingly, the penalty has the derivative of y hat with respect to x and derivative of y hat with respect to x, this and the second derivative. So both derivative and second derivative exist in the penalty or regularization term. And what do they mean? And I have L2 second squared L2 normal derivative here, and also here I have the Hessian of y hat with respect to x. What is definition of derivative? In the high school, whenever they wanted to teach us derivative, they talked about, the rate of change. Yes, exactly. How much, when I say derivative of A with respect to B, I mean by changing B, how much it affects A, how much change it implies on A. So it basically means this. How much my output is, how much my output is sensitive to my input, okay? Right? Am I right? With respect to x, y hat of x is the output of network. X is the input of network. The derivative of y hat of x with respect to x, it means if I tweak the input of the network, how much it impacts the output of the network. What does it mean? How sensitive my network is, how complex it is, how overfitted it is, right? When it is too much overfitted, recall that figure. I should bring this figure in your attention. Let me go back to that slide in the lecture of overfitting. That's an important thing to recall. Let me bring it. Where was that? I can bring it. Sorry, my device is a bit slow, but you need to be patient. Okay, here. This figure. We said if it is too much overfitted, then if I tweak one of my inputs, then it will come. I think in this figure, I had it. Which figure would? Yeah. So basically, I had a figure, I can't find it. So assume I have these points, okay? I have this line, okay? It's not overfitting. If I tweak this, assume I tweak this toward upwards, the line a bit changes. However, if I have a complex model, such as this, if I tweak this, the model completely becomes like this, completely changes its behavior. And now for a test data point here, around here, it will completely give me a different answer. So the more complex your network is, the more sensitivities to the input, training input. That's basically what I mean. Okay, that's why weight decay by our analysis avoids overfitting, because the penalty was on this behavior, was on the sensitivity of output with respect to input. So we are penalizing the overfitting, the complexity. Okay. Now let's go back to our slide. Yes. Okay. So that's very interesting. Now we understood why weight decay works. Note that the technique of adding noise injection works. Noise injection helps us avoid overfitting by our analysis. Note that the technique of adding noise to the input is also used in denoising autoencoders. I already talked to you about this. So in this figure, I said this is an undercomplete autoencoder, and this is an overcomplete autoencoder. I told you if I give x and my loss function, let's x hat to become very close to x, right? Forces a network. Then in the middle, in the latent space, it compresses data, okay? However, if I have an overcomplete autoencoder, if I say my last function is expectation of x hat minus x squared, L2 norm, the squared, then it simply cheats. It copies the input to the latent space and to the output, right? Because it have enough space in the middle, in the latent space. Then for avoiding that, I can add some noise to them. And then my output should be similar to x, not x plus epsilon. Then by this, I'm also training an autoencoder for denoising, right? That's called denoising autoencoder. And this technique, as we see, is also used for denoising autoencoders, noise injection. Okay, now let's go back, go to the next regularization technique, early stopping in neural networks. Okay, that's also very interesting. Although how we do it, it's easy. Its analysis is very insightful. You see that. Okay. As we mentioned in the explanations of overfitting lecture, we train neural network up to a point where the overfitting starts. Do you remember? So here I said, here this axis is model complexity, okay? And in iterative algorithms, such as a neural network, the more we train, the more complex we become. Therefore, you can see this x-axis as the iteration index 2, okay, like t. So either the x-axis is iteration index or model complexity. So in neural network, initially we are underfitting. The more we train, we reach some point where both validation error and training error are small. That's a good fit. But the training error goes down, but validation error goes up. Then we become overfitting. overfitted. In overfitted, we have overfitting, we have low bias, high variance. In underfitting, we have high bias, low variance. And the reason for this, which happens, is the complexity term, which we proved by Stein's unbiased risk estimator, or SHORE. We saw that the more complex we become, the validation error gets bigger, so it goes up, while we don't have this term of complexity in the training error, so it goes down. It continues going down. Okay. Now, what is early stopping saying? Basically, it says stop here. So because we can, after every epoch, we can calculate the mean training error and the mean validation error, right? We also have a log of previous validation errors and previous training errors of the previous epochs, I mean. Okay. So you can see whether the validation error is going up or not. Usually the training error goes down, maybe with some oscillation, but we can always track by our, assume in Python you have a list collecting all of the mean loss functions, these mean errors for validation and for training. You can even plot it. Okay. Then we can say whenever the mean validation error goes up, stop. But there's a problem here, a practical problem. What is that? So if you stop whenever the validation error goes up, it won't work. This might even happen in the first epoch or second epoch, because we have oscillations. Because it's not a convex optimization problem. It goes up and down, but the overall thing goes down. Okay. You can do several things. You can say if the last 5 times it goes up, for example, the last several times the validation error goes up, then stop. It means that the pattern is going up. Or you do some moving average. So by moving average, I mean you have a window that you move the window and you take the average of the window. Okay. In this way, your plot, your loss plot, gets smoother at least. Okay. So either do some moving average or take several last validation errors and check them, whether the pattern is going up or not. If yes, stop. That's called early stopping, because we stop early. Okay. When did it stop? I don't know what to do with my device. Okay. So now let's analyze it. Let's analyze it. Consider the regularized optimization problem in equation 5. J is a non-regularized loss function, right? Although you might say this was weight decay, right? But we will see that. Let me explain it completely. You will see that you can see early stopping as a weight decay. Why? Because you can see all of them as regularization methods. Therefore, you can analyze each of them as the other one. You can see early stopping as weight decay. You can see weight decay as noise injection to input to the weights. All of them. You can do that. And that's interesting. You'll see. Okay. So let's start with this equation 1. By the way, the L2 norm regularization is also called ridge regression or Tikhonov regularization. Tikhonov was a scientist, okay, working on that. Suppose W star is the minimizer of J, Therefore, by first order optimality condition, derivative of J with respect to W star, with respect to W at the point W star is 0, right? Is 0. Now the Taylor series expansion if of J is this. Why don't I have the second term which has a gradient in it? Because I'm considering the Taylor series expansion at point W star. So derivative of J at point W star, I know it's 0 because of first order optimality condition. So I don't have any term with a gradient in equation 7. and H is the Hessian. Okay. Again, do eigenvalue decomposition on Hessian U, delta U transpose. Right? U has the eigenvectors, delta has the eigenvalues. According to equation 7, what was equation 7? Here, the Taylor series expansion. So I have this. I have this J hat. I'm taking derivative of this with respect to W. Am I right? Just take it. Yes, I'm taking derivative with respect to W. So if I take derivative with respect to W, sorry, this becomes derivative of J. Derivative of J at point W star. And this becomes H times W minus W star. Why? This is quadratic with respect to W, right? W star is constant. H is Hessian. So it's quadratic function. So it becomes 2 times 2H W minus W star, but that 2 is cancelled by 1/2. So I will have this, okay? Again, by first order optimality condition, this is 0. So I will end up with this, H W minus W star. Okay, now we know backpropagation is gradient descent and chain rule. So gradient descent. Consider a step of gradient descent. It's this, right? W at iteration t equals W at iteration t minus 1 minus eta. Eta is the learning rate. Derivative of J hat with respect to W at the point WT. Okay. Now, what do? I just simply replace this with what I found here. Okay. So I will have this. Correct? Okay. Now, what do? Interestingly, these two terms are equal. So I left factor out. I left factor out these. So this is like I'm multiplying identity, because in multiplication, identity is not effective. So I minus eta H is here. I'm factoring it out. I'm factoring out that. Give me a second. That's correct, right? No, sorry. Here. So let me expand this so you will see this is correct. Let me expand it. So it is what WT minus 1 minus W star minus eta H W T minus 1 plus eta H W star. Right? Okay. I have minus W star in the left hand side. This is minus W star. So this is correct. This appeared here. This appeared here. And this appeared in the third term. So that's correct. Okay. Did you get it? In other words, what did I do? Here, consider this equation. I subtracted W star from the sides. Okay. And then I factored out. I rearranged the terms. Note this minus W star in the left-hand side. I subtracted. Okay. Now, let me write it down again. So WT minus W star, I have it here. This is what I found, but I replace H with its eigenvalue decomposition mentioned in the previous slide. Okay. I'm replacing H with it. If it ask me, is there any ambiguity? Yeah, please interrupt me, okay, whenever you. So this is so far clear. Okay, now what do? Assuming the initial weights, I want to start from W0 and then W1, W2, right? In gradient descent. Now assume the initial weights are 0 for simplicity in analysis. Okay, W1, so I'm putting T equals 1. W1 minus W star is what? I have this. So this becomes 0 because this is W0. Right? Right? This minus is here. Appears here. And I have this term. And this is W star. Okay, I just put t equals 1 and assume W0 is 0, you will end up with this. Okay, and then what happens? I just bring W star, this minus W star, to the right hand side, and I factor out the terms. I will end up with this. Okay, so now what do I do? What do I do? Interesting. See, what do I do? I have U, delta U trans. These are techniques you need to learn. I don't ask these proofs in exam. I just want you to understand. Okay, I'm saying this for you to understand why these are working in practice. Okay, so you have U delta U transpose. I have I here, identity matrix. So I can replace I with anything which is I, anything which is identity. Interestingly, UU transpose is identity because U is orthogonal matrix, non-truncated orthogonal matrix because it's the eigenvectors, matrix of eigenvectors. So I have UU transpose here. Okay, now I factor out, left factor out U because I have these, and right factor out U transpose. So U here, U transpose. Okay, and what happens then? So I'm repeating what we found here. Okay, now by induction, what do I mean by induction? So here W0 was 0, W1 is this, just set T to 2, and that set W1 to be this. Okay, do one more step. You will see that W2 becomes, W2 becomes U I minus eta V 2 U transpose W star. So the only difference is this square. Here we have power 1. Here we have power 2. By induction, we see apparently this power is T. Okay. Therefore, for WT, I have the power T. Okay. Now, what happens? Left multiplied to the sides, U transpose. Left multiply. Okay. Interestingly, U transpose U is what? I. U is an orthogonal matrix. So it goes away. This is I. And I have this. Okay. On the other hand, recall equation 2. Recall this. You remember? At the start of the session, we talked about it. Okay. Why? Because equation 2 was also used for equation 5. We have proved this in the lecture of overfitting, that the solution of equation 5 is actually this. Equation 10, this one. Okay. Then I left multiply to the sides U transpose. So I have this. And then this U transpose U also becomes identity. So we'll end up with this. Okay. This is on the other hand. This is not related to this. Okay. Then what happens? By some expression rearrangement asserted or claimed in the deep learning book of Jan Goodfellow et al. And Bengio in MIT Press. Okay. Reference 1. We accept that from Goodfellow. Okay. These can be rearranged to this. Okay. So equation 10. Now we want to compare equation 9 and equation 10. If you compare that, it will show you that this is an L2 norm regularization or weight decay. Also, we will see in a few slides that this is also early stopping. So you can see early stopping L2 norm regularization weight decay as either equation 9 or equation 10. Okay. I'm repeating them here. They are slightly different, but they are very related to each other. Now, if we compare them and they should be equal because from the same thing, we found two things. They should be equal. Okay. What is the difference between them, this term and this term? These should be equal. So it gives us equation 11. Okay. Now what happens? If we take logarithm from this expression and then use Taylor series expansion for log of 1 plus x. Just I also haven't memorized. Google Taylor series expansion of log of 1 plus x, it comes, okay? Search that. So what happens? First off, I'm taking the logarithm of the left-hand side. It's this. This t, power t goes behind logarithm. And this is the t here. And the rest is the Taylor series expansion of log of 1 plus x, right? What is x now here? It is minus eta lambda, right? So far clear? So the right-hand side now, this is the logarithm of right-hand side. It simplifies to this because logarithm of ab becomes logarithm of a plus logarithm of b. Also, this minus 1 powers goes behind the logarithm here. So I have this. Now, what do? I can write this as this. So I can factor out alpha. Again, I simplify this. It becomes this. Interestingly, these two terms cancel each other. So I will have only this term. I use the Taylor series expansion of this term. Again, Taylor series expansion of log of 1 plus x, but here x is 1 over alpha lambda. Right? This is a Taylor series expansion. Okay. Now, these, according to equation 11, these two should be equal. Equation 12 should be equal to equation 13. Right? What happens? How are they equal? If you compare them, you will see alpha should be 1 over t eta. Or if we rearrange that, t should be 1 over alpha gamma, alpha eta. Okay? So either t should be 1 over alpha eta or alpha should be 1 over t eta. It has a big analysis. It has a very interesting analysis. What is that? We found these two. Now you see why it is early stopping. Why? I think now you can guess, because early stopping is working with t, iteration index, t. Okay? What does it say? It shows that the inverse of number of iterations, which is important in early stopping, is proportional to the weight decay. So 1 over t is proportional to the weight L2 norm regularization parameter. What was alpha? Do you know? Alpha was here. In equation 5, it was the regularization parameter. Regularization parameter for weight decay, right? This is weight decay, right? Equation 5. So alpha is the penalty regularization term. Regularization parameter for weight decay. It means that how much weight decay is important. How much should I penalize weights compared to the actual cost? Okay. Interestingly, it is proportional to 1 over t. So, in other words, the more training iterations, the more t we have, the less we are penalizing the weights. So the bigger t, the smaller alpha. So the less we are penalizing the weights, and the more the network might get overfitted. What does it mean? Do not early stop. Do not early stop. Go for a lot of epochs. T goes up. It means that alpha is going down. It means that we are more prone to overfitting. However, if you do early stop, T goes down, alpha goes up. It means that we are actually doing regularization. Now you see the effects of them are the same. Interestingly. Moreover, some empirical studies, reference 14, show that noise injection and weight decay have more effectiveness than early stopping for avoiding overfitting. This is also an empirical study. You can take a look. So noise injection, they have seen empirically or by experiment that noise injection and weight decay have more effectiveness than early stopping. But early stopping has its own merits. It's used a lot. It's used a lot. Usually in industry, we do early stopping. Rather than weight decay and all of these things, we are lazy and we just do early stop. Okay. So now dropout. Dropout is also an important technique. Another technique for regularization. For understanding dropout, you should understand some concept in statistics. That's called bagging. Years ago, I think, many years ago, I always thought that bagging is related to bag. I'm doing some bagging. I'm collecting something in bag, but it's short. It's not correct. It's short for bootstrap aggregating. Okay. Bootstrap aggregating, bagging. It was proposed in 1996. You can take a look at reference 15. What does it say? It is a meta algorithm. What do I mean by meta algorithm? It means that you can use it with other algorithms. Okay. It's a meta algorithm which can be used with any model, classifier, regression, etc. The definition of bootstrapping is as follows, because bagging is bootstrap aggregating. For understanding bagging, you should first understand bootstrap. And bootstrap is also a concept in the statistics, in sampling. Suppose we have a sample, I goes from 1 to n. So I have x1 to xn with size n, where f of x is the unknown distribution of the sample. So xi, each of them, they are IID, they are independent and identically distributed with the distribution f of x. Okay. We would like to sample from this distribution, but we don't know the f of x. If we already know f of x, we can simply sample from it. One technique for sampling from the PDF or probability density function is what? A simple technique. If you don't know, take a look at that. You can see my tutorial on sampling. I have explained that there, but briefly talking about it, you have a PDF, make it a CDF, cumulative distribution function, and just sample from the inverse of CDF. Okay, so make a uniform value between 0 and 1, give it to the inverse of CDF, it gives you something, and that's the sample. So by sampling from uniform distribution, using the inverse of CDF, you can sample from some arbitrary PDF. Okay, that's a good technique in a statistics for sampling from a distribution. Okay, that's one thing. Again, what were we saying? Okay, let's go back to that bootstrapping. So I don't know f of x, so I don't know the inverse of CDF of CDF. So what do I do? Approximating the sampling from the distribution, I need to approximate it by randomly sampling from the available sample. So I have x1 to xn. I know its distribution is f of x. Using that, I want to sample from the distribution. What do I do? It's called bootstrapping. What do I do? In bootstrapping, we use simple random sampling with replacement. Okay. So I have x1 to xn. I sample one of them randomly, but I put it back. Assume you have a bag, not related to this bagging. So I have a bag. Some balls are in them. I put my hand in it and I take one of the balls. I read it, and then I put the ball back there. I shuffle again. I do this again. Okay. So this is called bootstrapping, and the sample is bootstrap sample. Okay. In bagging, what do? We draw, in bootstrap aggregating or bagging, we draw k bootstrap samples, each with some sample size. So did you get it? We sample a bunch of data points, okay, with some sample size. Then we train the model HJ, some model HJ. J denotes the index of model, okay? Using the jth bootstrap sample, and J goes from 1 to K. Hence, we have K trained models rather than one model. Let me explain this again. I have some data points, okay? I randomly take some data points, a bunch of them. I train some model. It gives me model 1. I put them back. I put the data points back to the data set. I randomly sample a bunch of them again. I train another model. We call it model 2. Model 1 and model 2 might be the same model, but trained by different data sets, or they might be different models. Anyway, they are different. Why? Because at least their data is different. But the models might be different too. So model 1, model 2, I do it for k times. I'll have model 1 to model k. Okay. Then what do we do? So I have k models which are trained. Also, for a test data point, I can feed it to each of the models. It gives me k prediction for that test data point. So I don't have one prediction now. I have k. The simplest way to do that is what? Some kind of voting or averaging, right? Some kind of voting or average. So I need to aggregate the results of the estimations of the k models for an instance x, test kx. So an aggregation model, easiest one is the average. Take the average. This is good for regression. If it is classification, then you take sign 2. So hjx gives you a score between 0 and 1. So sorry, -1 and 1, for example. Then you take this, the average is also between -1 and 1. And the sign gives you either it's class 1 or -1. Okay. Now, so equation 15 we already talked about. Let's go back. Let's go continue. Let EJ denote the error of the jth model in the estimation of the observation of an instance. Okay. So, as I said, we have several models. EJ is error of the jth model in the estimation, right? EJ. E stands for error. Okay. Suppose this error is a random variable with normal distribution having mean 0. So assume EJ is a Gaussian distribution with mean 0 and variance S. Sigma squared is S. And they are IID because the models are independent. Okay, assume. The noises are independent for the models. We denote the covariance of the estimations of 2 trained models using 2 different bootstrap samples by C. So what do I mean? The models might be correlated, might be dependent, might not be independent. So either they are independent or dependent. 2 cases might happen, right? Consider, let K be 2. So I have only 2 models. These 2 models are either independent or dependent. We are gonna analyze both cases. Okay. So in general, assume they are dependent. So they have some covariance. Okay. Okay. Clear everything? Now what happens? Expectation of EJ squared. What is it? I just told you. This is called equal to variance of EJ plus expectation of EJ squared. Expectation of EJ squared is 0 because the mean is 0. Okay. So this is S because of this, because this is this equals variance of EJ, and we know that variance of EJ is sigma squared or S, right? This is S. Therefore, variance is, again, according to this formula, you can rearrange it in this way. So this is S minus 0, it is S. Variance of each model is S. I think it was obvious from this. Doesn't matter. Okay, equation 17 was obvious. The variance of jth model is S because its noise is S. The variance of its noise is S. Okay, but now let's see their covariance. So covariance also, it can be proved. For more information, see the preliminaries in a statistical machine learning course. Covariance of EJ and EL. What do I mean by EJ and EL? The error of the jth model and the error of the elf model. Okay, 2 models. Is equal to expectation of EJ EL minus expectation of EJ times expectation of EL. Okay. What is this? I assume I'm denoting the covariance expectation of EJ and EL by C. I'm denoting it. So I put it C here. But each of these is 0. The mean of the E is 0 for all of them. So 0 times 0 is 0. So this is C. Therefore, their covariance is C. So the variance of each model is S. The covariance is C. But C might be 0. Might not be 0. Okay? We'll see that. We'll talk about it. Okay. So according to equations 15, 17, and 18. 17 and 18 are these. What is 15? Is this. Do you remember? This was a model aggregating the average. According to this, let's see. So variance of f hat of x, what was f hat of x? 1 over k summation, exactly. Summation of hjx, right? Again, there's a formula for that. So by the way, 1 over k here. 1 over k here is not random, but variance is quadratic. So it becomes 1 over k squared when we bring it out of variance. So this is 1 over k squared. Okay. Then I have variance of this term. Okay. This has a formula proved in the preliminaries of a statistical machine learning course. Take a look at that. So it is summation of variances plus summation of covariances, all pairs. Okay. So by the way, this 1 over k squared is multiplied to this, right? So it is multiplied to both terms. So I have this and this. The first here, this is variance of the models, summation of variances of the models. This is the summation of covariances of every two models. Okay. Now, what was this variance according to equation 17? It was each of them is S. Therefore, summation of all of them is Ks, right? This one, each of them is C, but how many summations do we have? Is it K squared? No, it's not. It's K squared minus the diagonal, because I'm not, see here, I'm not considering the covariance of everything with itself. It does covariance of, okay? So I'm not considering that in the formula. Therefore, it's K squared minus K. So K is, this is, K, we have K of them, but except the diagonal. So K squared minus K. So it's equals K, I'm factoring out K, is equals K times K minus 1. Therefore, I have K times K minus 1, but C of them. But each of them is C. Each of them is C. Okay? So I can write it in this one. Now, when we see its analysis, it blows your mind. Okay? I have taken this analysis from Professor Qudsi. This is his credit. Take a look at that. So I'm repeating it here. Variance of f hat of x is this. What does it do? The obtained expression has an interesting interpretation. If two trained models with two different bootstrap samples are very correlated, then C is almost S. So two models are very correlated, very similar. So the covariance becomes similar to the variance of one thing with itself, right? So C is almost S. If you replace C with S, this summation becomes S. Because what happens? Factor up, so you will have this, right? Then this addition becomes 1. Okay. However, if the two trained models are very different, very uncorrelated, the C becomes almost 0. There is no correlation between them. There is no covariance between them. You know, correlation and covariance are related to each other. Pearson correlation coefficient, right? Okay. Therefore, this becomes 0. This term goes away. This becomes 1 over K times S. Now compare equation 20 and equation 21. What does it say? Again, where did we start from? We have K models. If they are similar to each other, all of them, the variance becomes S, the variance of estimation. However, if the models are very different, very uncorrelated, the variance becomes 1 over K times S. What does it mean? If we have uncorrelated or very different models, it's better for us. The variance of estimation is divided by K. However, if our models are very similar to each other, it means that it's like we haven't done anything. We only have one model. I think it makes sense. If the models are very similar, why do we do it multiple times? One model is enough, right? This explains various things in machine learning, such as random forest. I talk about it in the statistical machine learning course. but this explains why random forest works. Just briefly in parentheses, it's not related to this course, but in parentheses, why is random forest, in addition to taking samples for the trees, decision trees, in addition to that, it samples from the features. Why? This is the reason. It wants to make the trees different as much as possible. So they are trained on different features of data. Therefore, it works. Otherwise, random forest reduces to one tree. Okay. Now we'll see that. I close the parentheses. We'll see that it explains why dropout also works in deep learning. So, as I said, I think I already explained this bagging. Oh, by the way, this also shows bagging is never destructive. It's either doesn't do anything like this, or it helps reduce the variance. So it's not destructive. That's one. And it also prevents overfitting because it reduces the variance of estimation. Do you remember? Overfitting has high variance. So bagging helps. Well, bagging is one of the techniques to reduce overfitting. Okay. And bagging can also be seen as ensemble learning. These are different terminologies in machine learning used for the same thing. Ensemble learning. For example, they say random forest is a type of ensemble learning because we have an ensemble of trees here, and some, or also in pure statistics, it's called model averaging. Model average, because they're, as do you remember, in bagging they were taking an average, they were aggregating. Okay. Now, one of the examples is random forest, as I said in reference 21. Another example is dropout in neural networks proposed in 2014, not far away from us. Okay. According to dropout, I think it was proposed by Hinton et al. In Hinton's team. Okay. According to dropout, in every iteration of training phase, every iteration. So dropout's behavior is different in training and testing. Okay. In training, in every iteration of training, the neurons are randomly removed with probability half, with some probability, such as half. So we have some neurons connected to each other, randomly takes some of them and randomly drops some of them. So if you remove randomly a neuron, what does it mean? All of the weights come into it and all of the weights going out from it are dropped or removed. They are not updated in backpropagation, right? It's like that you never had it in your neural network in that iteration. Okay, because for every neuron we have something like this, right? If you drop it, these and these, they are drops, the weights. Okay. And by the way, sampling, either dropping it or not with probability half, is like sampling from a Bernoulli distribution. Bernoulli. Okay. Bernoulli is like you're sampling your coin. Okay, this is a coin. Flipping a coin. This makes the training phase as training different neural networks. Now you will see its relation. So in each iteration, you're training a different neural network because you're changing the structure, a different neural network. As we have different models in bagging, so it's a kind of bagging. You're bagging different neural networks. Okay. In the test time now, what does it do in dropout? All the neurons are used, but their output is multiplied by P. Empirically, they have found out that this is good. This works. Okay. So P here, for example, is half. So you multiply every output by half. This imitates the model averaging of bagging in equation 15 because we are averaging several neural networks. Okay. By the way, this times half times P, as I said empirically they have found it, but in theory also you can understand intuitively why it is they are doing that. Equation 15, take a look at that. It's averaging, right? When you multiply the output of the neurons by P is like weighted average of the neurons, right? Because they are doing kind of model averaging in backend. Okay. Again, this reduces the variance of estimation as we talked about. So it helps. It's a regularization technique. It avoids overfitting. Okay. That's why people nowadays use dropout a lot. Okay. Also, in addition to our analysis, we can, in another way, we can say why dropout works well. Another analysis. Why? Because it imposes a sparsity. When you drop some of the neurons, the network becomes a sparse. Again, sparsity, betting on the sparsity principle, Occam's razor. As you see, we have this idea a lot, repeated a lot in different algorithms. So sparsity, by betting on sparsity principle and Occam's razor, it can be explained why it is working. Some acknowledgements. Some slides are based on our tutorial paper, the theory behind overfitting, cross-validation, regularization, bagging, and boosting tutorial, reference 26. Some slides are inspired by the textbook of Hasty, Tifshirani, and Friedman, Elements of Statistical Learning. Okay. Some slides are inspired by the book of Goodfellow, Bengio, and Corville, Deep Learning at MIT Press. Another textbook suitable for sparsity, because we talked about sparsity, is Statistical Learning with the Sparsity, the Lasso and Generalizations by Hasty, Tifshirani, et al. Some slides of this slide deck are inspired by the teachings of Professor Ali Qudsi at the University of Waterloo. Okay. References, very fast, we go over them. So this is a deep learning book. This is the paper in 1992 about weight decay. Weight decay, proposing the weight decay. A simple weight decay can improve generalization. Published in NeurIPS. This is modifying training algorithms for improved fault tolerance. I don't remember this one. What was for? You can take a look at the slides. This is for noise injection to inputs. By the way, I also in the previous session, I explained that you can see noise injection to input. You can also have noise injection to weights. They have the same impact, okay, to the weights of the neural network. So this is noise injection to the inputs in backpropagation learning in 1992. Okay, it's even before I was born, but it is very helpful. So here, the art of data augmentation. What is it for data augmentation? In 2001, this is also data augmentation in feature space. These are important papers I'm referencing. Okay, this noise injection, theoretical prospects about noise injection to input or the feature or the weights. This one, extracting and composing robust features with denoising autoencoders. This is about denoising autoencoders in 2008. This on weight noise injection training. You can see this is noise injection to the weights. Okay, in 2008. This early stopping, but when? This is a 1998. These are very first papers on early stopping. Okay, this one on early stopping in gradient descent learning in 2007. This one, overfitting in neural nets, backpropagation, conjugate gradient, and early stopping. Again, it talks about early stopping in 2001, also published in NeurIPS. When I say NeurIPS, whenever you see a paper in NeurIPS with high chance, not chance 100, but with high chance, it's a good paper. Okay. Convex optimization. It's a book of Boyd. That's a good book. Noise injection for training artificial neural networks, a comparison with weight decay and early stopping. See, people also at that time were in 2009, they were seeing that, oh, they can be analyzed theoretically the same. Noise injection, early stopping, weight decay. Okay. This one, bagging predictors. I apologize. Let's have a break. Let's have a break and then come back at maybe 20. a quarter or 20 minutes to 9, almost 15 minutes. So please come before a quarter to 9. Okay, so let's finish these references. So as I said, bagging predictors. This is about bagging. This is about bagging, and this one explaining bagging again in ETH 2000. It explains bagging again. That's good one. In Arkin classifier with discussion and rejoined by the author in 1998. I think that was related to bagging and model averaging and these things. Ensemble learning in 2012. This one, Bayesian model averaging. This talks about model averaging in statistics. It's a tutorial paper in 1999. This one, model selection and model averaging in 2008. This is a book in Cambridge University Press. You can take a look at. Classification and regression by random forest, 2002. This is the paper proposing random forest. This one, Dropout, a simple way to prevent neural networks from overfitting by Hinton et al. In 2014. This is the paper of Dropout. Again, this is the book of Hessian Tibshurani, and this is the sparsity book of Hessian Tibshurani. This one, the role of Occam's razor in knowledge discovery for Occam's razor in machine learning, and this is our tutorial, the theory behind overfitting, cross-validation, regularization, bagging, and boosting, our tutorial. Okay, let's go to convolutional neural networks now. Yes, okay. So regularization is over. Now we have talked about both regularization in machine learning general and also regularization in deep learning. And by the way, there is another regularization technique called Bash normalization, which I'll talk about in this slide deck. Okay, Bash normalization. So consider an image, okay? Consider an image with its pixels as the data for neural network. So now our data is not just a vector, it's an image, okay? If the neural network is fully connected, what does it do? It can't capture the 2D spatial correlation of nearby pixels. In simple words, what do I mean? Consider these pixels. Assume your data is an image with only 9 pixels, like this, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9. If my neural network is fully connected, which we talked about in this course, then what happens? I have 9 neurons. 1, 2, maybe 3 until 9, right? And what do? I reshape this to become, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I reshape it to become a column vector, right? However, as you see here, 1 and 2 are close to each other, neighbor with each other. Also here, 1 and 2 are neighbor with each other. So that's correct by reshaping. However, 1 and 4 are also close to each other. But here, 1 and 4 have fallen apart when reshaping. Again, you can see 1 and 5 close to each other. But 1 and 5 have fallen apart. So we have some two-dimensional spatial correlation between data features, but now we have ruined that. We only have considered one of them, maybe one of them in here, like 1 and 2. So vectorizing the data is destroying some of our information, right, in the input data. Therefore, people said, let's come up with a new structure of neural network called convolutional neural network, which takes input as it is, like this. We don't reshape it. Okay. So, as I said, multi-layer perceptron or fully connected neural network, we should reshape them. Therefore, convolutional neural network was proposed, and in short, we call them CNN. Okay, CNN was proposed to get the images as they are and not in reshaped form. In this way, the neural network can consider the 2D correlation of pixels. Okay, that's correct. CNN is a neural network which uses convolution in place of the general matrix multiplication in at least one of its layers. What do I mean? So in CNN, at least one of the layers, we have convolution in one of them. Maybe in all of its layers, we have convolution. Maybe in one of its layers or several layers, we have convolution. At least in one of them, we should have convolution. Okay. But the rest of the layers might be fully connected. So it might be a combination of convolutional layers and fully connected layers. Okay. And what do I do? What do I mean by this sentence? So do you remember fully connected neural network? We said, assume this is U1, this is U2, etc. Assume this X and this is f of X. Then f of X was U2 transpose sigma U1 transpose X. Do you remember? Sigma was the activation function in the middle layer, right? So we have matrix multiplication U1 and U2. U1 transpose, U2 transpose. Here, in a convolutional layer, rather than a matrix multiplication, we have convolution. And what is it? A CNN might or might not have one or several fully connected layers in addition to the convolution layers. Okay, let's see. CNN was initially proposed by Kunihiko Fukushima from Japan in 1980. Did you know that its origin goes back to Japan? Okay, in 1980, it was proposed, reference 1. That network was named neocognition in that paper, neocognition. Okay, and the idea of CNN was adopted and slightly modified for the task of handwritten digit recognition by a team led by Yan LeCun in around 1989. Yan LeCun is one of the important scholars in artificial intelligence. Okay, he's now in New York University, and also he's one of the bosses in Facebook, in the researchers in Facebook or Meta. And at that time, they had a project. I think they must have had some fund, maybe from government or another place, because most of their projects at that time were on handwritten digit recognition. What do I mean by handwritten? People draw the digits on paper and they want to find out what digits they are. Okay, many of their papers were about handwritten. Of course, they had some fun about this. Okay, so later, so they used that in 1989 in reference to Yan LeCun. Later in 1998, it was improved by Yan LeCun and Yoshua Bengio. Yoshua Bengio is in Université de Montréal here. He's also an important scholar in AI. Yoshua Bengio et al. And Yan LeCun, Bengio et al., they named that network LeNet. LeNet, okay, reference 3. Why? Why did they call it LeNet? It was named after LeCun. Le comes from LeCun and net is network, okay? LeNet. This paper, 3, was the paper which proposed modified NIST, or in short, MNIST dataset. This is the same paper that proposed MNIST dataset. Have you seen the handwritten digit dataset MNIST? This is the paper for that. And MNIST stands for modified NIST. NIST also is a dataset of digits. And it is a handwritten digit dataset widely used as a benchmark in machine learning nowadays. It's used a lot, okay? The structure of LeanNet is shown in this figure. So what does it do? It gets an input image, and then it has some convolutions, which we'll see. And then, so we have several, it produces several channels, several feature maps, okay? For example, six feature maps, each of which is 28 by 28. So the input is 32 by 32 pixels. Then it generates 6 28 by 28 ones. And then it does some subsampling. You can call it now, we call it nowadays pooling. We'll see that. And then it gives us some, so it downsamples the feature maps. And then we do again convolution, again subsampling. Afterwards, so we have 2 convolutional layers in LeanNet, and then several fully connected layers. Okay, this is what they had. So nowadays, many of the convolutional neural networks have kind of the similar structure. Usually, they have several layers of convolutional layers and then several layers of fully connected layers. Why do they need fully connected layers? Why do they need fully connected layers? First off, we will see that convolutional layers are sparse. So after several sparse layers, it's good to have some dense layers to have more parameters to learn. So they are by these, they are killing several birds with the same stone. What do they do? The first thing, they want to add to the learnable parameters so they don't underfit. Okay, that's one thing. Another thing is that at the end, I want to, for example, if I have 10 classes, I want to have 10 neurons. But in convolutions, they are 2D. I need to make it vectorized at the end. So in the middle, I need at the end, last layers, I need to reshape them to become like vectors, to have 10 neurons at the end. So that's another reason. The stages in a convolutional layer. So when we have a convolutional layer, there are at 3 stages, and these stages are the naming is adopted from the deep learning book of Goodfellow and Bengio et al. So what is it? Convolution stage, detector stage, and pooling stage. Okay, what is detector stage? It's the other name for activation function. Okay, we already talked about activation function in fully connected networks, right? So the only things which are new are convolution stage and pooling stage, right? Okay. First, let's talk about convolution stage. Recall filtering in image processing. Now, I want to tell you the idea of why, in addition to, do you remember I said at first I said they used convolution because they wanted to preserve the 2D structure of data. That's one reason. Another perspective to this, how they came up with this algorithm with convolution is this slide. Whenever you do some image filtering in image processing, computer vision, and these things, have you thought, okay, if I want to find edges, I use the kernel filter kernel of maybe Sobel or Perwit. Several filters exist for edge detection, just for edge detection. For example, Perwit filter, which was proposed in 1970 by reference 4. What is this? It has 2 filter kernels like this. By the way, what do I mean by filter kernel? So when we do filtering in image processing, I have some matrix for the filter. I call that filter kernel. This kernel is different from kernel in machine learning, like kernel trick, kernel SVM. This is kernel of filter. Okay, I mean this matrix. Okay, and usually in image processing, ancient image processing, there were some fixed values for the filter. For example, Prewitt said what? I want to find edges in the image. Usually edges are either horizontal or vertical, okay, or somewhere, or diagonal, whatever you call it, okay? Vertical, horizontal, diagonal. Diagonal is hard. Let's ignore it for now. Let's ignore it. Let's only detect horizontal and vertical. Okay, horizontal and vertical edges. So for horizontal edges, let's use this kernel. Why? Why is this working for horizontal? Assume I have, this is in my image. So of course, if I do edge detection, I should detect this, right? Only this, right? Now, if I apply this filter on the image, what happens? Here is bright. Here, suddenly I have a change of lightness or whatever color. Okay. And here is the same also. So here I have a jump in intensity, in color, whatever you call it. Okay. In pattern, I have a jump in this way. Now, this is showing exactly where the jump happens. Above are the same. In the middle, there is edge. Below are the same, but the above and below are different. So it's detecting the horizontal edges. Likewise, with same analysis, this is vertical edges. So like this. I want to find this edge. So these ones are one side, these minus ones are one side, and this is in the middle. Okay. And this is 3 by 3. We can have larger kernels of filters, right? So Previtz proposed this. Another scholar, I think that at that time, people said, oh, we can change these values and propose a paper, publish a paper, right? Sobel did that. Okay, several people proposed. So for example, some people said, okay, rather than this one, let it be 2 or something. So they were proposing different filters and they were working. Some filters, if you have passed an image processing course or computer vision, I think you have seen those. Some of them are for edge detection. Some of them are for corner detection. Some of them are for sharpening the image. What do I mean by sharpening? Strengthen or magnify the edges. Okay. Or some of them are for smoothing. It means that opposite. Make the edges smooth. Okay. So there are various filters in image processing. Fixed values. Now, someone came and said, why do I need to put fixed values in my filters? Why don't I learn the best values for the filter? Rather than using the predefined values in the filter, let me learn it. Again, for learning, what should I use? Tell me. For learning in machine learning, what should I use? For learning anything, I should use optimization. I should have some cost. I should do optimization. So the translation of their word was what? Let me find the best values of filter by optimization. One of the ways for optimization is gradient descent. Gradient descent and chain rule is backpropagation. So let's learn the best weights in the filter, the best values in the filter by backpropagation. However, backpropagation works on the weights of neural network. So I can assume these values, the values in the filter are the weights of neural network. Right? So far clear? So I have filter, the values are learnable. I want to learn them by optimization, by backpropagation. Backpropagation is applied on the weights of neural network. So let me consider the values of filter to be the weights of neural network. And that's exactly a convolutional layer, okay? Convolutional stage. So, yeah, and they are used for feature extraction for my own task. My own task might be classification, regression, whatever, clustering. I'm saying that for my own task. And how is my task determined? By my loss function in the neural network. The loss function determines my task. So I'm telling to the neural network, hey, neural network, consider this loss function. For my loss function, find the best filter kernels, values in the filter kernels in these layers. Okay. Now I think you understand convolution better. So that's the way. Therefore, let us learn the best kernel, filter kernel values using optimization for our own task and our own data set, by the way. So the weights, the task might be the same, but I change the data set, but the values will change. So for my own data set and my own task, find the best filter values. Okay. A convolutional layer considers the values of the filter kernel as learnable weights of that layer, which can be trained by the backpropagation algorithm. Okay. The discrete convolution is defined as this. What is it? A of t. This is the notation for convolution of x and k, and t is the index or time, whatever you call it, but in it is discrete. Okay. So it's summation of a goes from minus infinity to infinity, x of a w t minus a. This is a convolution. As you see, I have minus a here rather than I don't have a minus t. I have t minus a. So it flips one of them. Okay, it flips one of the signals. Okay, for those of you who have passed the course signals and systems, maybe in electrical engineering or computer engineering, you have seen this a lot. Okay, but this is a discrete convolution. We often use convolution in more than one axis at a time for a 2D image I. So assume I have a 2D image I, so I can do a 2D convolution rather than 1D convolution. So let the kernel of 2D filter be denoted by K, the kernel, the matrix. Okay, guys, listen. The 2D convolution is this, Sij. What do I mean by Ij? Ij is element of S. So this is again convolution of I and K. What do I mean? This, I have an image, I have a filter kernel. So I convolve these two. I and K, Ij. We have two summations, so nested summation, I, M, and N, K, I minus M, J minus N. So again, I have flipped the kernel twice. Once in this around one axis, once around the other axis, right? Where the summation is over the number of rows and columns of the filter kernel. Okay, if it is 3 by 3, so we have 3 summations here, and summations over 3 elements and summation over 3 columns, rows and columns. In other words, in a convolutional layer, we do not consider convolution in all range minus infinity to infinity, but only in the range of kernel size. So when we are doing it in image, when we are applying kernel, convolving a kernel on the image, we don't consider the whole minus infinity to infinity, only in the range of the kernel filter. Okay, I assume in the other parts it's 0. If you put 0 for the other terms in this equation 2, it becomes equation 3, but for 1D. Okay, we can assume that the summations in the convolution are in all range, but our signal is 0 after the size of filter kernel filter, right? So this is my filter kernel. All of their other parts, we assume it's 0. Then the summation is behaving only to be in the range of the filter kernel. Okay. Convolution, another note. Convolution flips, as I said, flips the kernel, one of the signals. In convolving, you need to flip one of the signals, either the image or the kernel. Okay. One of the signals, such as the kernel filter. Usually, we are lazy. Usually, we do not flip the filter kernel in the convolutional layer. In image processing also. In image processing, we are lazy. We do not flip. And we just multiply the elements of the kernel by the image. So we are using cross correlation. If we don't flip, it's called cross correlation. We are approximating the convolution by cross correlation. Doesn't matter. Especially in image processing, it doesn't matter. Why? Because if I know that what is the already flipped kernel, I flip that already. So when I'm convolving it, I don't flip it. You know what is its flip. So already set it to be the flipped one. Then you don't need to flip it. In image processing, this is the way. In machine learning, In convolutional layer, we don't care. Why? Because whatever you put, the back propagation learns that. If you flip it, it will learn to flip it. If you don't flip it, it will learn not to flip it. The only thing is important, which is important, is the weights to be learned. Okay? Again, sometimes laziness is good. Okay? So compare a dense or fully connected layer and a convolutional layer. Now I'm gonna analyze convolution. So this is fully connected layer. This is convolutional layer. I think fully connected layer is obvious. But why is convolutional layer like this? Can you tell me? It's because this is the input, but I'm moving one kernel, filter kernel over the pixel. So this is one kernel filter. I'm moving it one to the down. Again, moving it. Did you get it? So this is one kernel filter, applying one. Again, in the next step, I move it one to the down. Again, one to the down. It's the same filter kernel. I don't change the filter kernel. As I don't change it, I'm using it the same, but I'm sweeping it. It becomes like this. Let me clear it so I think you see it better. Okay? It becomes like this. As seen in this figure, the convolutional layer is sparse. Just compare these two. It's sparse. Again, betting on the sparsity principle, Occam's razor. Okay? Because of these, as it is sparse, it works well. So in a fully connected layer, every output neuron interacts with every input neuron. However, in a convolutional layer, there is a sparse connectivity and thus a sparse learnable weights. We have a smaller number of weights. We have a smaller number of weights. Okay? This sparsity, again, is beneficial for betting on the sparsity principle and Occam's razor. And also, being low rank. Low rank learning is also an important topic in machine learning. When you learn your matrix to be low rank. Why? Because, again, using Occam's razor, when a low rank matrix can do something, why do you make it the full rank? Let it be simpler. Okay? So the weight matrix will probably have lower rank compared to a dense layer. Okay? As obvious in the above figure, this sparsity occurs because the kernel is usually smaller than the input size. Do you agree? Consider this case. I have 4 inputs. My kernel size is also 4. Yes. So it becomes exactly like a fully connected layer. I don't want to draw all of them. If the kernel size is the same as the input size, then you are multiplying everything by everything. I think let me tell you in this way. Give me the second. Yes, I think that's correct. Consider, you should note one thing. I have an image, okay? I have a kernel filter with the size of input. I multiply elements of the image by the kernel filter once, okay? You might say, okay, in this case, if I have 3 inputs, 3 kernel size, it will be like this. I agree, but you move the kernel. You move the kernel one by one. It means that you're multiplying every pixel by all of the elements of this big kernel. If the size of kernel is the same as input, you are multiplying everything by everything. Then it becomes like a dense layer. Okay? If the kernel size is the same as input size, the layer becomes a dense layer or fully connected layer. If the number of input and output neurons of a layer are m and n respectively, okay, then so m is the input, n is the output. Okay, then the fully connected layer becomes O its complexity, O m by n, big O notation. Okay, it required a space and also number of parameters. That is why if the kernel size is k, where k is less than m, the input size, the runtime is OK by n, where k is less than m, so its complexity is lower. It's learnable parameters, and also its required space is lower than the dense layer. Okay, that was analysis of complexity and these things. Okay, now there is another constraint, so I'm analyzing it in another perspective. There is another constraint in a conditional layer, and sorry, this needs to be convolutional layer, and that is parameter sharing. What is it? Because as I said, we are moving the same kernel filter. So if this is the kernel, I move it, then it becomes like this. So this and this are the same weight value. Also, these are all the same. These are also all the same. In fully connected, these are not the same. In a dense layer, these are not the same. But in a convolutional layer, we are sharing parameters. Okay, not only it's sparse, but also some of them are shared. Okay, in other words, we sweep the same kernel over the neurons in a convolutional layer. In a traditional fully connected layer, every element of the weight matrix is multiplied by one element of the input. That is, it is used once when computing the output of a layer. In a convolutional layer, however, every element of the kernel is used at every position of the input. We are using it every time, right? The same value. Instead of learning a separate set of parameters for every position, we learn only one set, only one kernel, right? Another analysis. Another property of the convolutional layer is the equivalence property of the convolutional operator with respect to translation. What is equivalence property? That's in pure math, okay? A function f, I think in category theory, one of the fields of mathematics, so you can also find this topic. So a function f of x is equivalent to a function g of x if f of g of x is equal to g of f of x. So what is it? In this figure, I have taken this figure from Wikipedia. So x by g, for example, goes to x, and then by f goes to y. You can go either in this direction or in this direction. First, convert x to y by f, and then y to y by g, something like that, okay? The convolution operator has equivalence property with respect to translation. That's interesting. So you can see that you can translate the image input and then apply convolution, or you can apply convolution and then translate the image. They are really will be the same. Okay, this is one of the properties of convolution. Okay, I'm not going to prove it here, but this is one of the properties of convolution. If you translate, then convolve, or you convolve and then translate, they will be the same. And that's very interesting. This is exactly what we want in machine learning, right? Note that convolution is not equivalent with respect to some other transformations, unfortunately, such as rotation and changes in scale. Okay? We will see in a few slides how we become more robust to translation. We'll see that. Okay? Important parameters in the convolutional stage. So these are some parameters: stride, width, channels, padding. These are important. Okay, what are they? Stride is just a step of jump of kernel in convolution. What do I mean? When you convolve a kernel filter on image, then you move, you sweep your kernel on the image. With how many pixels do you move your kernel and do the next convolution? How many pixels or how many features in both directions, X and Y, do you move your kernel? Okay, that's called a stride. The smallest one is 1. You only move 1 pixel. Okay, and as you see, the kernel, the convolutions will have overlap with each other, depending on a stride. You might set the stride to be too big, so you don't have any overlap. Okay. Then width, the kernel filter might be 3 by 3, 5 by 5. Usually it's odd. Okay. Usually it's odd, but it might be even. Doesn't matter. If it's even, like, just give me a second. For example, it's 4 by 4. We usually take this as the middle one. Okay. We usually take this pixel as the, so this is the middle, right? The actual middle, but it's not a pixel. It's not, it's in the middle of kernel. It's, we need to take one of these cells. So this, we take usually this as the middle. Okay. But it's usually odd. Padding, oh, channels, number of channels. So it's the depth of the kernel. They also call it the number of feature maps. So you should, it's important not to confuse the number of channels of input and output. So you might have several channels in the input, but you have, for example, if you have 3 channels, and then you have, for example, 3 by 3 by 3, a 3 by 3 by 3 kernel. You can apply this on the 3 channels, and it gives you a feature, one feature map. Here we have the number of channels, or the number of feature maps is 1, because we only have one output, one feature map. But the number of channels in the input were 3, right? What do we mean by number of channels here, or the number of feature maps? We mean how many kernels do we have. So in each layer, who says we should have only one kernel filter? Who says that? Simultaneously, I want to learn 9 filters, each of which extracts some important features. Did you get it? In every layer, rather than having one kernel filter, let me have 9 of them, several of them, each of which will learn will take some of the role, some of the responsibility. One of them will say, okay, let me extract the edges around the nose. One of them says, oh, you do that, so I do the other one. I will consider the color at the top right. One of them says, okay, you took that, I will take another responsibility. So each of which are taking some responsibility in extracting features. Okay. The number of these kernels is called the number of channels, or the number of features. Okay. So we have the number of channels in input, a number of channels in output. The number of channels in output shows how many kernels we are learning. Padding. Also, you have seen it in image processing probably. What do I mean? Assume I have a 9 by 9 image, okay? Then I apply a 3 by 3 filter on it, edge detection, whatever you call it, pre-width, double. Then it becomes at the end, I think 8 by 8, am I right? Or 7 by 7, something. The number of pixels reduce. Why? It's because of this simple example. Assume this is your input image, okay? And I'm applying a 3 by 3 filter, okay? This is my corner pixel. This is my corner pixel, right? When I apply a 3 by 3 filter, I put it here at the start. My middle will be here. So I'm replacing the middle with whatever I apply the kernel on. So I'm ignoring all of these. I will not have one initial row, one end row, one initial column, one end column. They will be dropped after filtering. If you do it several times, you will shrink in the size of the image. In order to avoid that, they will add fake features or fake pixels around the image. There are several ways to do that. The simplest one, the most lazy one, is what? Adding zeros. So you put zeros there. Another one is mirroring. You just, for example, you have 0.7 here, just put 0.7 again here. Another way is mirroring from the other one, from the other side. It's like the image is like a cylinder. So at the end, you have 0.7, put 0.7 here. So there are several techniques for padding. The simplest one is zero padding. Just put 0. Okay. Why do we need zero padding? Again, we don't want to shrink it. Okay. And we are doing filter in convolution. We are convolving the filter. So zero padding, mirror padding, etc. Okay. Example of convolution with one channel of input. I can't see it. Just give me a sec. Give me a second. Okay. So I put a link here. You can also see it at home. I put it in a slide. This is an example, a GIF, okay? So what is it doing? This is a kernel matrix. Assume at this iteration, so far, the values have been learned like this. They might change in the next iteration, okay? If it was in image processing, these values would be fixed. But in machine learning and deep learning, they change. These are the values that we are learning by optimization, by backpropagation. So for now, for this iteration, we have this from the previous iteration. Then I sweep this kernel over the image. With here, stride is 1. What do I mean? I move 1 pixel to the right and also 1 pixel to the bottom. And then what do I do? Every time I multiply these values to the pixels which fall in the kernel. Okay. So for example, 0 times, here it shows the computation. Here it shows the computation. For example, 0 times something, -1 times 105, something like that. Then you will have 9 values right here because it's 3 by 3 kernel. Then add them. This gives you the one scalar value, right? Then in the output, replace the corresponding value for the middle of the kernel in the output. Did you get it? This is what is happening in convolutional layer in a graphical way. Okay, this is for one channel of input. For one channel of input, because assume your input is grayscale image. You have only one channel, right? One grid. What if your image is RGB? So in initial layer, you have 3 channels, for example, RGB, red, green, and blue. In the middle layers also, what happens? For example, from the previous convolutional layer, your number of features, the number of feature maps were 9. For the next layer, the number of input channels will be 9. You might start from one channel as the data, like grayscale image, but in the middle, you might have 9 channels. So for the next convolutional layer, the number of channels will be, input channels will be 9, right? That's one. So an example of a 3 channel of input in convolution. Give me a second. It's here. It's loading. Hopefully it works. Yes. See? Consider this. There are 3 channels of input, RGB. What is W1? What is W2? W1 is one of the kernels. W2 is another kernel. So here in this example, the input channels are 3. The output channels are 2. So the number of feature maps is 2. You see? W1 is one matrix of learnable parameters. W2 is another one, which we learn both of them by backpropagation. And now I think you see why neural networks can be parallelized on GPU. You can learn W1 on one GPU for W2 and another, do they depend on each other? No. Right? So you can parallelize that. Okay? So, and you see the kernel here is maybe here, the kernel size is what? 4 by 4 by 3. Okay? 3, you don't need to tell your code that it's 3. It already finds out. The input is 3 channels. For output, you should say to the code how many feature maps you want. I want 2. Okay? Okay, I think it's obvious now. Now, where is this? Okay, let's continue. Detector stage. Detector stage is another name for activation function. This is because they act like they detect the signal. They detect the signal if the signal passes from the threshold. Do you remember initial neural networks? They were using binary activation function. Maybe that's why they call it detector stage. We already talked about it before in the course for fully connected layers. Pulling stage. What does it do? In pulling the stage, pulling is performed. What is it? Pulling provides a summary statistics. This is a terminology in the statistics. It means that it summarizes your signal. Okay. What do I mean by summary? We have various ways to summarize data. One of them is mean or average. One of them is maximum. One of them is minimum. One of them is median. One of them is weighted average, and these things, right? So simply it provides the summary statistics from the signal. Some examples: max pulling, average pulling, weighted average pulling, median pulling, L2 norm pulling. Let's see some examples here. For example, max pulling with a stride 2 and width 2. What do I mean? Here, consider these. Take the maximum of them. It's 2, 1, 2, 3. Which one is maximum? This 3. Then a stride is 2. Jump 2. So note that for convolutional stage, we had a stride, we had width. For pulling also, we have a stride, we have width. They shouldn't necessarily be the same, right? So the stride is 2. Now width is also 2. That's why the kernel, I put it like 2 with width 2. Width and height are usually the same in kernel. So with stride 2, I will come here. The maximum of 7, 5, 2, and 4 is 7. Do it for here. The maximum of 8 minus 1, 7, and 3 is 8. The maximum of minus 5, 1, 2, and 6 is 6. So that was max pulling with the stride 2 width 2. Now average pull. Average of 2, 1, 2, 3 is 2. Right? Average of 7, 5, 2, and 4 is 5.5. Likewise for other elements. And average pull now, the stride 2 width 2. So sorry, this was average pull. This was median pull. Median of 2, 1, 2, and 3. What is that? I know these are too simple, but let's practice. I know it. You are graduate students, but let's go through them so everything is clear. 1, 2, 2, 3. The median is here, which is neither of these elements. So it's average of these two. 2 plus 2 over 2 is 2. Okay. So likewise. So I think it's obvious. We can do median pull, average pull, max pull with some stride and some width. Okay. What do I mean by weighted average pull? Then it means that multiply each of these by some weight and then take the average. Then L2 norm pulling, what do I mean? Consider this as a vector of 2, 1, 2, 3. Take the L2 norm of this vector. Right? L2. So it's like the length of the vector containing the elements of this. Okay. So again, we have a stride, we have width, we have padding, we have number of channels again for output. Okay. So by the way, according to a stride, we might have overlapping or non-overlapping pulling. That's is used a lot in deep learning literature. So when we say again, according to the stride, we might have overlap between what we have, or we might jump and there is no overlap. Okay, I think it's obvious. Again, padding, we can have zero padding, mirror padding, right? We might not have padding also, doesn't matter. So let's see some other examples here. Okay, thank you very much. Thank you. So we might have, so for example, I appreciate. So here, for example, max pull with a stride 2 width 2 is, we already saw that in the previous slide. Here, max pull with a stride 1 width 2. What do I mean? Consider this is 3. The maximum of them is 3. But with the stride 1, so it's overlapping. So it's like this. Maximum of 1, 7, 3, and 2 is 7. And likewise, etc. Max pull with a stride 1 width 3. What do I mean? Width 3 is like this. Okay, and it's etc. Here, I'm not doing any padding. We might also do some padding. So here, if we do 0 padding, then we can have max pull stride 2 width 2. It becomes like this. For example, after padding, so I'm padding all of these rows and first rows and last rows and first columns and last columns, right? So here, then you can say my stride 2 width 2, it becomes like this. For example, maximum of 2, 1, 0, 2, 1, 2, 3 is 3, etc. By the way, the 0 pad also can have some widths. How many pixels do I pad? 1 pixel, 2 pixels, 3 pixels, etc. Okay. I know these are very easy, but important to know. So pooling stage. By the way, for you to get the grade easy, maybe I put one of the questions in the assignment and this is to be like this. I just want you to get the grade, doesn't matter. Okay, so pooling stage is what? Pooling makes the features almost invariant to local translations. So one of the analysis of the pooling. So we already had analysis of convolution, now the analysis of pooling. So what is it? Pooling makes the features almost invariant to local in translations. So it's good for becoming robust to translations, right? How? We will see that. I think this example explains why. Consider this is input of pooling, like max pooling, whatever. This is the output. Okay, so input is 0.1, 1, 0.2, 0.1. I shift the input a bit. So I shift 1 to the right. So this 0.1 becomes here. This 0.1 becomes here. This 0.2 becomes here. This 0.1 goes there. And something comes from left, which is 0.3. Okay? Obvious? Now, let's do max pooling for before shift and after shift. The maximum of something 0.1 and 1 is if this something is less than 1 is 1. Then the maximum of 0.1, 1 and 0.2 is 1. The maximum of 1, 0.2, 0.1 is 1. The maximum of 0.2, 0.1 and something, if that something is less than 0.2 is 0.2. Okay? Let's shift it. The maximum of something 0.3, 0.1 is 0.3 if it is less than 0.3. The maximum of 0.3, 0.1, 1 is 1. The maximum of 0.1, 1 and 0.2 is 1. The maximum of 1, 0.2, 0.1 is 1. Here, if you compare the input, all of the features have changed. Now compare the output of pooling. Only these two have changed. Rather than changing 4 inputs, only 2 of them changed. So it means that we became more robust to translation. We dampened the effect of translation, right? From 4 to 2 here in this example. So in most cases, it is good to become invariant and robust to local translations. But in some applications, it may be destructive. So don't always use pooling. See what you're doing. Maybe it is important for you to know where it is happening exactly. But if you don't care where it is happening in the image, then do pooling. You want to be robust to translation. But maybe you are having a task where you exactly want something to happen somewhere. Why do you do pooling? It's destructive. Okay. It is usually helpful because we usually want to know whether a specific feature exists in data, but we don't care where exactly it is. Such as this. I have 5 here. If I move 5 to the right, to the left, I want it to be only recognized as 5. Okay. Pooling also helps in downsampling data. That's one of the things that pooling does. Okay. This reduces the representation size and hence the computational and the statistical burden on the next layer. Example, like this. Assume the width of pooling is 3. The stride is 2. So this here, the stride is 2. The width is 3, right? Correct? So what happens? The width is 3. The stride is 2. Here, from 1, 2, 3, 4, 5, 6, we became only 3. 3 values. So it helps downsampling. If you recall Linet in the initial slides of this slide deck, they used pooling for downsampling. They called it downsampling, right? Right? Another analysis of pooling, another one. We can see both convolution and pooling stages, both of them, as infinitely strong prior. What do I mean by infinitely strong prior? I mean, by this figure, I think it's obvious. Assume you have a prior distribution on your data. So you have some weak constraint or weak prior like this. You can make it stronger. It means that reduce the variance. So it's more concentrated on where you are, like this. Or you might become infinitely strong prior. So you put all of these to 0 except around it. And as you see, convolution does that because, as I told you, in convolution, we only convolve in the range of kernel. We assume the other parts are 0. Pooling also does that, only in the range of pooling kernel, right? So it is applying some infinitely strong prior, but why is it useful? Again, sparsity. The sparsity, between the sparsity principle and Occam's razor. Okay. We can also dynamically, so there are other ways to do pooling. We can also dynamically pool the features together rather than pooling the neighbor features together only. Because so far what we saw, only neighbor features were pooled together, right? But who says that we should pool only the neighbor pixels or the neighbor features? Who said that? Maybe if I pool this feature with that feature at the end, they work well. So let us find which features we should pool. How? By clustering. Clustering algorithms such as k-means on locations of the interesting features. I'm not saying the details of these techniques, I'm just introducing to them. For more information, see the papers. Reference 10. So we can pool the features in the same cluster. It was proposed in 2011. Okay. In this way, different sets of pooling regions will be used for different data inputs. So some data comes, data input. We see, oh, by the way, these features should be pulled. For another data input, some other pixels or features should be pulled together. We can rather learn a single pooling structure, and then we apply that learned pooling structure to all data inputs. So rather than that, we can also learn some pooling. So this is for this question that I'm saying. So for the first item was for the question of why we should pool only neighbor features, right? The second bullet point is for this question. Who says I should only do max pooling, average pooling? Why do you fix the type of pooling? Max pooling, average pooling. Let me learn the type of pooling by backpropagation also. So one important thing in deep learning is that you shouldn't only restrict yourself to learn the weights of neural network. You can add some more learnable parameters and learn them by backpropagation also, while you are learning the weights of neural network. One thing is learning the type of pooling, right? So you can learn whatever you want in deep learning. So let me learn one single pooling structure and then apply it on the all data inputs, proposed in 2012, reference 11. Okay, another thing, good thing about pooling is that so far in fully connected layer, in convolution layer, we assume that the input is the same size, right? Especially for fully connected, it must be. In convolution, at least you can say, I convolve, so I don't care what size I have. But usually in coding, you see that they should have the same size. But pooling can help you handle different sizes of input. How? By this example. Assume you have a big image, so you use a big pooling kernel for that. It becomes like this. If you have a small image, you use a small pooling kernel for that. It becomes like this. They become the same size. Because pooling is a summary statistics, provides summary statistics of big image and a small image, right? Of course, it drops a bit of accuracy, but at least it makes them the same size. Okay, batch normalization. Batch normalization was proposed in 2015 in reference 12. What does it do? What does it do? It can be used in various network structures. That's important. So fully connected, convolutional, whatever, including fully connected convolutional. So it's not just for fully connected, for convolution. It helps prevent covariate shift. I will tell you what it is. And hence, it helps generalization and avoids overfitting. First off, don't be scared of the name covariate. Usually in the statistics, they call the data covariate. Okay? For example, in regression, we have X and labels Y, right? X is the input data. They call X covariate. Okay? So don't be scared of that. That's it. What do I mean by covariate shift? That's exactly, it means domain shift. Domain shift. So, for example, you have some training data points. Either you have several mini batches, and one mini batch has, for example, some mean and some variance because it has some distribution, right? Your next mini batch has another mean and variance. So there is domain shift or covariate shift, whatever you call it, between these batches. They don't have the same probability distribution. That confuses the network. Once you give some batch with some mean and some variance to the network, it learns something. Then you suddenly give something else to it. It confuses. For example, I'm a human. You tell me for going to washroom, I should go from this side. I go a bit, and then I ask again in the next epoch, in the next iteration. I say, where should I go? You should go. You say, go from the other side. I will get confused where the washroom is. Okay. So let's make the batches the same probability distribution. This is the idea of batch normalization. Therefore, it helps generalization and avoids overfitting. It prevents covariate shift. It helps training to be faster too. Empirically, they have shown that it makes it faster to train. So assume the input of layer is x d-dimensional, x1 to xd. Okay. So the layer has d neurons, right? This layer. For a mini batch, now come to the mini batch setup. For a mini batch, let the input of the layer to be set xi. I goes from 1 to b, right? And each xi is a vector, d-dimensional vector, x1 to xd. Okay. B is the batch size. Okay. Do you remember mini batch stochastic gradient is? Let xij denote the jth dimension of xi. So we have b vectors, each of which has d dimensions. So xij, let it be the jth dimension of xi in the batch. Okay. So xi is xi1 to xid. I mean this. Batch normalization, what does it do? First off, it is applied for every layer. So every layer, if you say in this layer, I want batch normalization, it is applied on that layer, not the whole network. Okay, whatever layer you apply batch normalization, it is applied on that layer. And then what does it do? It standardizes or applies Z-score normalization on the mini batch in that layer. So what do I mean? Do you remember in machine learning? This is important. In machine learning, there are several ways to normalize data. I will finish it in a few minutes. Just give me some time. In machine learning, we can normalize data in several ways. One of them is min-max normalization. What is that? It says it makes the range of data to become maybe between 0 and 1 or something, to become some range by, I think, subtracting from mean, right? Something like that. It doesn't matter. Oh yes, x minus mean over max minus mean. Okay, this is mean max normalization. So it becomes all of the data points, training data points, become between 0 and 1. Another way is Z-score normalization, also called standardization. So what is it? It says x minus mu over sigma, I think, sigma. So what is it? Mu is the mean, sigma is the standard deviation, sigma squared is the variance, sigma is the standard deviation. What does it do? X minus mean over the standard deviation. It makes the distribution of data Gaussian, standard Gaussian, the standard normal, with mean 0 and variance 1. Okay, so batch normalization does that for a mini batch, for every mini batch in that layer. What do I mean? You feed the mini batch to the network, it passes through some layers, and it reaches that layer. The input of that layer, you have, for example, if the mini batch is B, you have B of them, right? You have Bx1 to xt. So in other words, each xi is the input of that layer, not the input of network, input of that layer. Okay. Then for every feature, batch normalization standardizes every feature separately. Okay. I have D features, D neurons, D features. So I use D times. So I have for each of them, for J goes from 1 to D. I have mu J, the mean of the features, the Jth feature across the mini batch. This is the variance. The sigma J squared is the variance of Jth feature across the mini batch on that layer. Both of them are a scalar, right? Because it's one feature. So then xij minus mu j over this. This is square root of variance. So it's a standard deviation. However, I have plus epsilon in the denominator inside the square root. Why? For stability. Why? Because I don't want to have division by 0. What if the variance is too small for the coding part? Okay. This is what batch normalization does. So it's important. It applies on every feature in that layer across the mini batch, and it does that for every mini batch. Okay, the next things we will cover, we'll continue. So what is the agenda? We will talk about initialization of kernel. There's just a few other slides in this slide deck. So we'll talk about random initialization in neural network. Its theory is what? It has theoretical analysis, random projection, and Johnson JL lemma, Johnson something lemma. I can't pronounce it correctly. Random projection, and also another way to initialize the kernels by PCA, principal component analysis. Afterwards, we cover the important convolutional neural networks such as VGG, ResNet, DenseNet, Inception, GoogleNet, some other AlexNet, and these things. So we'll cover important ones, which usually won the ImageNet competition. After they were mostly proposed by Google, Facebook, etc. Afterwards, we will cover recurrent neural network, LSTM, and then we go to attention mechanism and graph neural networks and some other state-of-the-art algorithms. We'll also cover reinforcement learning, deep reinforcement learning. Okay, thank you. soon I will upload your assignment, and I will make announcement for forming the teams. Okay, thank you.
Of course, yeah.